Nate Allen here. Just wanted to give you guys a little background knowledge on inverse circular functions and hopefully make it very clear for you. Do a few examples and then let me know if you have any other questions. Here we go. So first thing I wanted to do is ask you, first of all, what does the word inverse mean to you? And I put a little funny GIF on there for you since we're going through a weird time right now. Keeping our distance, learning this way. But I put a summary of the inverse function and what it actually represents. This doesn't just go for trig functions, but all in all. And so we'll kind of discuss that and what it means to be an inverse. That's just a fancy math term for reverse. And so in this case, if we just switch all the inputs and outputs, which are typically our x and our y values, then we know that we have found the reverse of what we normally would have had originally, usually denoted as f. And so our inverse function, the symbol that we use is f to the negative 1. So we typically write it like so. One thing we got to make sure is that in order for something to be a function, it has to pass what is called the vertical line test, meaning we're going to test every x value, which means we draw a vertical line for that particular x to see if it gives us only one output, one y value. Well, when we switch all the x's and all the y's, then everything is reversed, hence the name inverse. So now we need to make sure that we have what is called a one-to-one function, meaning what about the other direction? What about for every y? How do we test to see if we only get one x value out once we've done the reverse and switched all the x's with all the y's? And so in that case, we use a little thing called the horizontal line test. And so that's what that finds for us, is whether or not a function is actually one-to-one, meaning that we know it's a function, so it passes the vertical line test, but when we switch the x's and the y's, will we have a function when we find the inverse as well? All right, and so one thing I just wanted to make sure that you're all aware of is you previously in algebra knew f to the negative 1 to represent the reciprocal. Anytime we had a negative exponent, we flipped it, in other words. Unfortunately, in math, we sometimes repeat things. And so in this case, we are repeating that symbol to also represent the inverse. And so what we're going to start with here is our sine function, right? And so if I was to ask you to graph y equals sine x, then hopefully you remember that it starts at 0, and at every quadrantal angle, pi over 2, pi, 3 pi over 2, and 2 pi, we can find those values and everything in between to get the graph of sine. Now, obviously, we can rewrite this instead of y equals as f of x because we know it passes the vertical line test. It is indeed a function, and we can test that very simply by choosing different colors and testing whether or not it is a function. And we can see for every input x value, in this case angle, we get out one y value output. And that's why we're able to write it as f of x. However, if we wanted to find the inverse of this thing, all right, well then what happens? Well, unfortunately, you can see if I just draw one horizontal line, it fails. And it fails in a lot of places. So what we have to do, and why we're doing all of this, is if I was to continue drawing this out on the other side, not just the positive, but 0, 1, 0, negative 1, and 0, and I drew it over 2 periods, you see it would fail even more miserably if we're looking at the horizontal line test. So what we have to do is look and think about what would be the best way to find answers. And so why this all comes up is, what if I was to ask you this question, all right? And I gave you a certain input and output. So going back to sine and looking at the input, which is an angle x, typically in radians, and then an output. So if I asked you the sine of what value gives me an output of 1/2, hopefully you all have those reference angles memorized, and you should all be able to say pi over 6 or 30 degrees, right? And so the way that we like to rewrite this in a little bit faster form is rather than leaving something blank, what we're really looking for is the unknown to be by itself. And so what we'd like to do is reverse the input and the output. And in order to do that, I would put the sine of 1/2 equals what? Angle, which we originally called x. And so that you know that 1/2 is actually a ratio, usually typically, excuse me, our output, well then now I need to put this little -1 to let you know that, hey, this is reversed of what we normally had. This is still going to be my y over r, and this is going to be my angle in radians, of course. And so this is our shortened version of saying this. I can just rewrite this as sine inverse of 1/2 and ask you, hopefully you can recognize, anytime that you see an inverse in trig, that means you're trying to find an angle, theta or x if they want it in radians. So this is really what we're looking for, is what angle gives us this ratio of 1/2. Okay. Now, a situation occurs when we think about this a little bit deeper, that we know that all students text in class, right? Hopefully not. But there are two places, unfortunately, where sine is actually going to result in positive outputs, ratios. And that's in quadrant 1 and quadrant 2. So which answer am I asking for? Do I want the one that is 30 degrees in this quadrant, or do I want the 30-degree reference angle in quadrant 2? Well, you wouldn't know. And so whatever we do, we want to make sure that we all get the same answer. And so we have to decide what obviously would be an easier quadrant to work with so that we get a positive answer for sine. And hopefully you all say quadrant 1 without a doubt. So we're going to toss quadrant 2 for the positives, which means if I was to change this to negative 1/2, well, then I also have two quadrants. So which of those two do you think would be the easiest to utilize? Quadrant 3 or quadrant 4, because they both yield negative answers for sine. And hopefully you would recognize quadrant 4 would be the best, along with quadrant 1 for our positives. Because everything in quadrant 1 we know is acute, 0 to 90 degrees. And everything in quadrant 2 is also acute, but negative, 0 to 90 degrees. So in this case, it really helps us to stay in quadrants 1 and 4 and not 2 and 3. Now, going back to the whole thing that I started with for inverses, if you remember, we had to pass the vertical line test to make sure that it is a function, which we know sine passes with flying colors. But what about the horizontal for our one-to-one functions for our inverses? Well, if we take away all the rest of this and just focus on quadrant 1, and then we took away all the other, all the way to quadrant 4, which would actually be there, then you can see that I actually have a graph that would pass there, anywhere. And therefore, we have now restricted it to quadrant 1 for all positives and quadrant 4 for all negatives. Now we can look at the same thing with cosine and doing something similar. And what would be really nice is if we did that same thing for cosine and it worked just like sine did. But remember, this one is graphed a little bit differently. And doing the same thing here for our quarters. You notice if we were to look at quadrant just at positives and negatives, right? And we were looking for the positives for sine, we would be perfectly good with using quadrant 1 again for anything positive. But if we looked at quadrant 4 and tried to use the negatives, you can see that's where cosine is also positive. So unfortunately, we cannot use that. So again, it's narrowed down to quadrants 2 this time and 3, but we're never going to use 3. If we have a choice, we'll use quadrants 1 and 4 because those are both acute. But unfortunately, we couldn't because of cosine being positive in quadrant 4 as well. So unfortunately, we have to use quadrant 2 to get negative values. And so looking at our graph again, if we were to try to get rid of everything, so now I don't need anything over here, and I could look at quadrant 1 and quadrant 2 and get rid of everything here. Now you can see that, yes, indeed, it would pass that horizontal line test, and therefore we would have a function in quadrants 1 and 2 for the inverse of cosine. And so in this case, we're going to go and explore some more of our other graphs. But the cool thing is, if you think about the inverse of sine and the inverse of cosine, for all the positives, we'll use quadrant 1. But for the negatives, it's a different story. We would like to use quadrant 4 everywhere for negatives, but like we said, we can't do that for cosine. So we said that we would use quadrant 2 instead. Well, what do you think would happen if we used the reciprocal functions of these things? And so very quickly, I won't explain it as in depth. What if we looked at those types of equations like tangent, cotangent, or even secant and cosecant? Well, you can see here, if I just graphed one period of tangent and cotangent, we're already set. These things would pass very easily the horizontal line test. And so in this case, we're definitely going to use quadrant 1 and quadrant 4 for tangent. But I could use for cotangent quadrant 4 as well if I drew it over here. But the problem would be that we would have this vertical asymptote in play. And so in this case, for a cotangent, what would be the easiest so that we don't have a gap about 0? We're just going to use quadrants 1 and 2 as well for our positives and our negatives. Okay? And I'll summarize all of this in a minute. What about cosecant and secant? Well, remember, cosecant is actually the reciprocal function of sine. And we knew sine could use quadrants 1, definitely for positive. We'll use that for every single one of them, so that's easy. The only thing we really need to worry about are the negative values. And so in this case, because cosecant is sine, we obviously will not be using that. And word to the wise, we never use quadrant 3 for any of these. So we will use this for positive and this for the negative values, just like we did for sine. Because cosecant, the only difference is the reciprocal. Everything's flipped. So in this case, also, we can do the same thing similarly over here for secant, because we know that that is the reciprocal function of cosine. And using our positive, negative values, we know that we will always use this for positives, never this, quadrant 3. So we got it narrowed down to quadrant 2 or quadrant 4 for negatives. And because we're dealing with the reciprocal function of cosine, then we cannot use quadrant 4. So instead, we're going to have to use quadrant 2 as well for the negative values. Now, if you looked at that again over here, you can see why we do certain things. Quadrants 1 and 2, in this case, we're using this and that. And although there is that asymptote, it holds exactly like it did for cosine. So that's going to be a easier way to remember it. Same thing over here. If we use quadrants 1 and 4, although we're going to be using quadrant 1 and quadrant 4 about that asymptote, it's just easier because it's the reciprocal function of sine. So if we go to tangent and cotangent, again, you can see quadrants 1 and 4, and then 1 and 2. So the good thing is we got it narrowed down to all of these. And so I just have the charts here for you in the summarization of all the stuff that I just explained. And remember, we write inverse as the -1. And notice we put it after the sine or the cosine because that's what we're using the inverse of, not the actual angle x. But because that can be a little confusing and we have a lot of weird types of things that we use with trig, like radian measurements and pi and things like that, they also created this thing called arc, which is another way to say the inverse. So whether you see the -1 power after your trig function or arc in front of it, that means that we're finding the inverse. And remember, anytime that you see inverse, what you're going to be trying to find is not what we normally would be given, which is the angle, and us giving them based off of that reference angle, the output value, the y over the r, the x over the r, what have you, the 1/2s, the √3/2s, the √2/2s. Now, whenever we're trying to find the inverse, we're going to be giving them the angle, which means they're going to have to give us the ratio. And so that's why I really harped on you all to memorize all of those reference angles early on, because they're not going to go away. And so here's a synopsis of the entire thing that we just discussed. And you can see that I'll try to highlight in similar colors. Sine was in 1 and 4, which is what we preferred because we can use all acute angles. The other ones that are in 1 and 4 are tangent and cosecant, which is just the reciprocal function of sine. Okay, and remember the reason for those is when we're looking at the positive versus negative, we know that we're dealing with positives there always. And then the negatives would be in quadrant 4 for those. But when dealing with the other functions, all of them still for positive, but this time we cannot use quadrant 4 because of cosine. So that's why cosine and its reciprocal function, secant, we'll use 1 and 2. And then also cotangent because of its graph and passing the horizontal line test. So pretty easy to remember sine and its reciprocal function, cosecant, as well as cosine and its reciprocal function, secant. The only ones that behave a little bit weird are, of course, tangent and cotangent because of the same reason of their graphs. They have different types of graphs than the other ones. So keep that all in mind as we progress, but not too bad. Unfortunately, more stuff to memorize though. So let's look at some of the types of examples that we all can see. And the first one here, I bolded for the emphasis of making sure that you answer real numbers. And notice, since it says arc or to the -1 power, meaning inverse, we're trying to give them now angles instead. So it still might be written as y equals, but you need to know whenever it says arc, you're trying to find an angle. In this case, we're trying to find the angle for sine that gives us √3/2. And hopefully we all remember the angle for sine that gives us √3/2 would be, I'm pausing for dramatic effect and hopefully to let you remember, the angle for sine that gives us √3/2 would be 60 degrees, but because they asked for it as a real number, y, then we're going to have to give them the result as pi/3. Okay, and for those of you that don't know, there's a nice shortcut in order to find all of the sine, cosine, and tangent. You can either look it up and use your fingers, or you can check out another video that allows you to just do sine of an angle, cosine of an angle, and then use your reference angles. This also works for tangent, but 0, 30, 45, 60, and 90. All of our quadrant 1. And just to remind you all, you start at 0 and then just increase by 1. Then for cosine, which remember it's named cosine because it's the co-function of sine, meaning it's a complementary angle, you're just going to do the complement to this and do it in reverse order. Now, if you do this, it'll save you half the time it would if you memorized it on your own. All you got to make sure that you remember is that you have to take the square root of every single one of these. And that will give you every single value for both sine and cosine for every reference angle. To tell whether they're positive or negative, simply use our chart. So when looking at this, you got to be careful because it is asking for the inverse of sine. We're looking for the angle now that gives us 1/2. And if we look at that, we can see right here, and hopefully you all have it memorized, is 30 degrees. But remember, because it's negative, we got to be careful and make sure that we give them the real number value, so radian measurement instead of degrees. That would give me a negative. And we said, if we can, we always want to stay in quadrants 1 and 4. And with sine, we're all good with that because we know it's negative in quadrant 4. So remember, we're going to just use a negative 30 degrees or negative pi over 6 to give them our answer. So what you got to be very careful of is when doing things like this one where they might try to trick you a little bit. Because remember, when we did our graph of sine, it would oscillate from 1 to -1. And so when we graphed this, the highest values that you could ever have, the maximum value we call it, is 1, and the minimum value would be -1. So in this case, when you see something like √2, remember that is the ratio that comes out, and because it's the inverse, we're looking for the angle for sine that gives us √2. And if you don't know what √2 is, you can always use a little thing called the squeeze theorem, where you squeeze it between two numbers you do know. You know the square root of 4 is 2, square root of 1 is 1, so the square root of 2 is something between 1 and 2. And in this case, because it's bigger than 1, and in this case less than 2, that's irrelevant in this case though, but because it's bigger than 1, then we know that this does not exist, right? So be careful that they don't try to fool you into thinking that there is an angle that gives you the square root of 2.